All right. All right, hang tight. I'll be back in a second. Hey, did you guys have any difficulty logging in today? They wrote to me over the weekend saying they were going to institute some new security features on the UTexas Zoom links. They said they were going to start instituting passwords to log in, but as far as I know, that hasn't happened yet. So. Hey, where do you guys put these little pictures that show up as your like avatar? Where, is there a setting for that somewhere? I didn't see that one.
I think it's only when you don't have webcam on.
Oh, okay.
Well, maybe, I'm not sure. I haven't played with it yet. I haven't played around with it yet.
Okay. I don't know what I would use anyway. All right, it's not quite time to start, but if somebody has like one of the homework questions that you want to ask me about, or anything that you've been struggling with, you've been trying to do some of the reading.
Yeah, someone already asked a question in chat.
Oh, okay, let me pull up the chat. What was question 7? Let me pull that up. I think I had that on my screen. Waiting for Quest. Yes, Question number 7 is a great question, but I don't want to do it yet because we haven't talked about other coordinate systems besides Cartesian coordinates. Well, I mean, that is part of what I wanted to talk about today, but I guess I do want to make sure that you guys are okay with things like question 6, I guess, is the triple integral. We did some triple integrals last time, if I remember correctly. Let me put that down here. Okay. Yeah, all right. So let me spend a little bit of time on some of these triple integrals, because if we do it in the right way, if I get you guys used to saying the right sequence of words to set up your integration problems, all of that stuff will transfer over to other coordinate systems like the one that had to do with cylindrical coordinates. So let me focus for a few minutes on, I think it's question number 6 on the homework. Somebody was asking me about it over the weekend. And it gives us an example to, it's a triple integral, so it gives us a chance to practice setting up the limits of integration there. But if you, well, just bear with me. We'll do the triple integral and then I'll show you how the same thing will work in other coordinate systems too. So let me swing this over and get my, oops, my document came apart. Set up. Something's wrong with my display. There we go. All right. So question, I think it was question number 6, asked you to do an integral over, I have to compute some integral over the set S, where S is now a subset of 3-dimensional space. So we, as always, the integral means you're going to split the set S up into little parts, and then you'll multiply the value of the function at one point within each one of those parts and multiply by the size of that piece of the set S. If S is a 3-dimensional set, then the size would be measured as the volume of that piece. So we write dV in there to indicate that we're going to measure sizes by volumes. And specifically, they gave you the function was equal to, I think it was 8z plus x or something. It may have been different functions for different people. And the set S was described as being the region, well, here, I'll just write the letter S again, but I'll try to draw it for you. My 3D pictures are kind of lousy. But here, I'll label the axes in 3-dimensional space. They wanted you to look at the set that was bounded by a few simple surfaces. There's, first of all, the XY plane. That's going to be the bottom. And the XY plane is the set of points where the Z coordinate is equal to 0. So there's a first equation. That's one equation in 3 unknowns, X, Y, and Z. 3 minus 1 is 2, so that's a surface. Next, there were a couple of planes. Let's see, let me draw one here. They gave you the equation X equals Z, or Z equals X. And again, I want to stress that that's actually an equation that links 3 variables, X, Y, and Z. So one equation in 3 unknowns is again a surface, but this one is just a plane. Since it doesn't mention Y, you can draw this plane by finding the corresponding curve, the line, in the XZ plane, and then just stretching it parallel to the Y-axis. That'll turn out to be the top. This will be the bottom, this will be the top of our shape. There's another plane involved. That's the set of points where X and Y coordinates are equal. If I write the equation Y equals X, you're used to thinking that that's a line in the XZ plane, but it also stands for a plane in 3-dimensional space. So I'll think of that as the back surface of this figure. And then finally, there's one more surface that'll be I'll call it the front surface of this figure, and that's found by following along the parabola y equals x squared, I mean, the parabola swings on the other side of the y-axis as well. But since, again, this one equation in 2 variables can also be thought of as one equation in the 3 variables, with z not really being mentioned, it just stretches this parabola up and down. And it's really only the up that matters for us because we need it to stay above the xy plane. So I'm going to find the place where this, how should I do it? There's a parabolic surface now, but if I follow where that surface meets this previous plane, the plane where z is equal to x, then that'll give me a sort of a roof line on a 3-dimensional figure that follows this curve as well as this straight line segment. That straight line segment is where the plane z equals x, I'm referring to that as, maybe I should write the word in here, that's the roof. This one is the floor. Then that curve and that line segment together give me the boundary of my entire roof. This parabolic surface, you notice it's tall here and skinny over there. That's the front face. The back face is a triangle, and the bottom is sort of a half moon. Excuse me. All right. So I wanted you to see the different surfaces, 4 different surfaces that intersect to make the boundary of this region. To do our calculations, it may be easier to try to throw all of those surfaces away and just have you focus on the building that I've just created that has a roof and a floor and a front face and a triangular back face. So there's the set S. All right, and as always, you need to remember what the meaning of the integral is. We're going to split this into small pieces, multiply the volume of each piece times the value of the function in there. Now, Fubini's idea is to give us a way of splitting the set S, simply because we have the Cartesian coordinates out there. A natural way to split this is to draw not just the plane where the z coordinate is 0, or where the y coordinate is 0, or the x coordinate, but rather draw a lot of parallel planes, all the places where any one of these coordinates stays constant. That means taking this 3-dimensional figure and chopping it up with some slices perpendicular to the y-axis, slices perpendicular to the x-axis, and slices perpendicular to the z-axis. And that would split the set S up into a zillion little boxes that are all lined up with the coordinate axes. They have faces that are parallel to these coordinate planes. There's a very natural way to split the set S up. It's not the only way to split S up, but it's the natural choice if you're using Cartesian coordinates. When you do that, if I could zero in on one of those little figures, those little boxes, you made a box by looking at this portion of the set S as being the set of points that lay between 2 planes that were perpendicular to the x-axis. So the front face of this box might be the set of points where x was equal to 1 constant, and the back face is the set of points where x is a different constant. If you do that, then you can figure out the length of this line segment that goes between those 2 planes. That would just obviously be C1 minus C2 or C2 minus C1. We call that length dx. And in the same way, you are further limiting your box by looking at it as the region between the planes where y is held at 1 constant value or another one, and the distance between those 2 planes would be called dy. And of course, the same thing that in the z direction, that would be called dz. So Fubini's suggestion is that you split the set S up into a zillion little boxes that are found by looking at the region between the sets of points where each of the coordinates takes on 1 constant value and another, And then to get the volume of the little piece, the size of the little piece, you multiply together those differences between the two x coordinates, the differences between the two y coordinates, and the differences between the two z coordinates. So that's Fubini in action. He's suggesting that you rewrite this little bit of volume here as being a product of little bits of x's, little bits of y's, and little bits of z's. You're still going to keep evaluating the same function over and over, 8z plus x, at points within each of the different boxes. And then when you're done, you'll add, as for lots of different values of x, you'll add the value of this function times one of these products, where first you let the x's vary, and then you let the y's vary, and then you let the z's vary. You take sums, this is a big long S for sum, and computing the sum over all possible ranges of x's and y's and z's, that gave you the integral. That's the spirit behind Fubini's theorem, and it was easy to prove in the case where the set S was just a single box. But even when S was a varying kind of shape, like the one we have here, we've learned that we can get, we have ways of writing this integral out as a triple integral, an iteration of 3 one-dimensional integrals. We can have the variables in any order, in fact, but we do need to get the right limits of integration. And this is the second main idea that I've been trying to work with you guys on, is how to find those limits of integration. Of course, how you do it will depend on the order in which you write the variables. With the 3-variable problem, you have 6 possible orderings to choose, and they won't all be equally easy, equally useful for you. With some experience, I'm going to suggest in this case that you put the variable x on the outside, y in the middle, and z on the inside. It's still a triple integral problem, but now the choice is to have limits of integration on x on the outside, y in the middle, and z on the inside. Oops. With your function expressed by exactly the same formula as we started with. That part never changes. Now, here's what I want you to say to yourself every time you're trying to set up these triple integrals. And the reason that I'm going to go through it again is because as we move into things like cylindrical coordinates, I'll be able to use exactly the same language to help you get your limits of integration, even in that setting. So, if we've made the decision that we're going to compute our integral with the variables in this order, the first order of business is to get the limits of integration starting from the left here, starting from the outside and working our way inwards. We actually compute the integrals from in out, inwards out. But we'll get them from the outwards in. So you need to walk over this entire set S and talk to all of the points in there and ask them for their x coordinates, and then report to me the least and the greatest values that you get from any of those points. So here I go. I'm just talking to all the points inside here, asking about x coordinates. Now, to put this picture back into the coordinate system, you know that the way you're going to get your maximum x coordinate is to go as far as possible away from the yz plane. And to get the minimum x coordinate, you go as close as possible to the yz plane. You go in that direction. So it seems clear from the picture that your maximum x coordinate would be the x coordinate of this point, or equivalently of this point up here. Actually, all of these points have the same x coordinate. But these are the points that are furthest away from the YZ plane. They have the largest x coordinate. And to get the smallest x coordinate, I guess it would be this point all the way in the back. I guess you can already see that x coordinate is going to be a 0, but I'll come to that in a second. So having identified the point or points that are going to give me my maximum x coordinate, now I have to figure out the value of that x coordinate. So to get the x coordinate of this point, I'm actually going to have to figure out all 3 of the coordinates of this point. I can get the 3 coordinates as soon as I can get 3 equations. And I can get 3 equations as soon as I can say 3 things about that point. So to me, the way that I would describe this point is, it is the point where the roof meets both the front and back walls. It's this point over here where the curvy front wall meets the triangular back wall and the roof. If you say it that way, then that tells you three things about this point. The fact that it's in the roof means that its coordinates have to satisfy the equation for the roof. The fact that it's in the front face means that its coordinates satisfy the equation of the front face. And the fact that it's also on the back face means that its coordinates satisfy the equation of the back face. So now I've written down three equations that restrict the coordinates of this point. Now you got three equations and three unknowns. The solution set should be zero-dimensional, 3 minus 3. That means it should be a finite number of points. In fact, this is easy enough to do. Once you know that y is equal to x, the middle equation here would say that x has to equal x squared. There's only two real numbers that are equal to their own square, namely 0 and 1. So one of the points would be to have x equals 0, in which case y is 0 and z is also 0. That's this point here. Or the other possibility is to have x equal 1, in which case this equation says that y is equal to 1, and this equation says that z is equal to 1. So I said three things about this point. I got three equations that describe the point. I now have the three coordinates of this point, and in particular, I know this point's x coordinate. So I did all of that work to be able to fill in this one blank. Now, the next thing you have to do is to move to the inner integral, the middle integral, get those limits of integration. And when you do that, as soon as you cross over this square bracket, you're going to start holding x fixed. Holding x fixed, in our case, means looking at the points within this figure that have a fixed x coordinate. Now, having a fixed x coordinate, I was drawing such situations over here. I was holding the x coordinate fixed at one value or another. And you notice that these are planes that are perpendicular to the x-axis. So you need to imagine taking this figure and slicing it with a set of points, slicing it with a plane that goes perpendicular to the x-axis. I don't know how good your visualization skills are for a three-dimensional thing, but if I can, I'll redraw the relevant portions of this figure. There's that part and that part, and down below is this straight line. Kind of looks like the front of a canoe or something, but it's got the top is actually a part of a flat plane. I guess canoes come up higher in the front. And also you do need to let it all comes together as a point in the back. All right, now when I hold the x coordinate fixed, I'm intersecting that with a plane like this. Here's the way I should draw it in that case. I'll draw the plane first, and then take, for example, that straight line segment that's at the bottom. That starts somewhere in the distance. It pierces the plane once, and then it continues further in front of the plane. Likewise, this curve on the bottom is a parabola that starts at that same starting point on the right at the origin, actually. And then it pierces the plane, and it continues through further. Joining those two curves are both part of the xy plane, the floor, and that whole floor will intersect this plane in a line segment. Well, actually in a line. If this is already the set of points where x is held constant, then there's the floor of our picture is a set of points where the z coordinate is 0. Since I'm holding x constant, I don't need to pay a lot of attention to the x coordinates in this picture. I only care about the y coordinates and the z coordinates. And so the set of points where the z is equal to 0, that now represents a line, not a plane. It's just a line within this plane where x is equal to constant. And within that line, I've identified a couple of points of interest to me. These are both points that have a z coordinate equal to 0, but their y coordinate is the other one of interest in the picture. What I know about this point's y coordinate is, well, it lay on that line of points where the y and x coordinates were equal to each other. So if you're currently in the plane where x is held constant, then the y-coordinate is also equal to that constant. So the y and z coordinates of this point are c and 0. In the same way, this point over here, why is this point here? This was a point where this plane met that parabola, or more precisely, it met the floor, which had z equals 0, and the parabolic wall, which was the set of points where y was equal to x squared. So if you've held x to be a constant, that means I know the y-coordinate to be c squared, and the z-coordinate is still 0. Now there's more to this thing. This plane, I'm intersecting this plane where x is a constant with the original figure. When it does that, it's going to meet this triangular back wall. That back wall was part of the plane where y was equal to x. The plane y equals x intersects my plane, my other plane where x is a constant. The two planes meet in a straight line. The equation of this straight line is, I hope you're not surprised, y equals x. It's the exact same equation. You could write it as y equals c, because we're holding x constant in this figure. And now you recognize that as being a straight line in the yz plane. When you let y be a constant, that gives you a vertical line in the yz plane. This is the z-axis here. This is the y-axis. Likewise, this one. Why is this? What have we got here? This line that I just drew now is the rest of the surface, the rest of the intersection of this front surface, this curvy front surface here. It's the intersection of that surface with my plane x equals a constant. The surface.
Excuse me, Dr. Watson?
Yes, go ahead.
Could you please move up the paper?
Oh, yes, certainly.
Thank you.
This front surface, you know, I got it by just stretching a parabola straight up and down parallel, in the direction of the z-axis. So it effectively consists of a bunch of vertical posts all nailed into a parabolic curve. But in particular, when you look at a point on there that has a fixed x coordinate, the whole intersection is just going to be a vertical line. The intersection of this plane with the original surface, y equals x squared, is this vertical line. Only a portion of that will be in our 3D shape S, but this whole line, I can even tell you the equation of it. Again, no real surprise, the equation is going to be y equals x squared, which you could write, if you wish, as y equals c squared, because, again, we're holding the x coordinate constant. Finally, there's the roof of my figure. The roof of my figure was a plane, x equals z. Where does that intersect this current plane, x equals a constant? Well, two planes intersect in a straight line, and I don't know if you can see it geometrically, but maybe you can see it from the equations. If x is supposed to equal z, but at the same time, x is supposed to be held constant, that means that the equation of this line right here is just z is equal to a constant. That is a horizontal line in the yz plane. You have your choice. You can write it as z equals a constant or z equals x, because that c just stands for the current value of my x coordinate. So here's the thing. To figure out more limits of integration, I held the outer variable constant. I look at all of the points in my original figure for which this coordinate is held at some constant value, somewhere between 0 and 1. I look physically at what that set looks like. And now I scan this set only, and I talk to all of these points, and I ask them about their y and later their z coordinates. So where do you go to find your lowest y coordinate? If you're in the yz plane, then your lowest y coordinates are the coordinates of the points going that way. So it would be all of these points that are tied for having the lowest y coordinate. And then the greatest y coordinate would be the y coordinates of the points that are found on that edge. So all of these points happen to be tied for the least and the greatest values, for the greatest value of the y coordinate. Now you need to find out what the coordinates of these points are. So here's a point that I will choose as my winner. That's one of the points that has a maximal y-coordinate. Whatever y-coordinate I get, it's going to go right in that box. I'm going to get that y-coordinate by getting all three of the coordinates of this point. I'll get the three coordinates by getting three equations. I'll get three equations by asking me for three things that I know about this point. And here they are. The first thing that I know about this point is that it lies in this plane where I'm holding x-coordinate constant. The second thing that I know about it is that it was also on the roof. It was on that other plane where the z and x coordinates were the same. And the third thing that I know about this point is that it lay on that triangular back edge. That was the plane of points where the y and x coordinates were equal. So three statements about the point lead to three equations that describe the coordinates of the point. And those three equations I can now solve to get the three coordinates, Cartesian coordinates of this point. Whatever the x coordinate is, the y coordinate has to be the same, and the z coordinate is also the same. So whatever your current x coordinate is, that's the number that will go up here. And I've been saying c in the last couple of days. You could also just write it as x, because actually x and c are synonyms at this stage of the game. Down here, I'm going to write down the minimum y-coordinate that I see anywhere in my set. That's the coordinate of any of these points. You might take this point as your representative. And that's a point that lies on the floor, but it's also on the curving front wall. And of course, it's on this plane. Everything that we're doing right now is taking place in this plane. Three equations. That gives me three coordinates. Obviously.
Dr. Messon?
Yes?
Thank you.
And of the three coordinates, the one that I want right now is the y-coordinate, so that's what goes in here, c squared, or I'll just write it as x squared. To get the last set of coordinates, you would then now hold y also as a constant value, and now look at the portion of just this picture where the y-coordinate is fixed. So if we previously were down to this much of a figure, we had this single plane with the y and z axes in it, but we've discovered that the portion of the set S that we're interested in within that plane was just a single rectangle. Now I'm supposed to hold the y-coordinate fixed as well. Well, the set of points that has a fixed y-coordinate is just a vertical line, and the ones that happen to be in my set S now are going to be just a line segment. If you hold this y-coordinate fixed at some value, I don't know, d, then all that's left is to figure out the least and the greatest values of the z-coordinate. So that would be the highest and the lowest values, the z-coordinates of the highest and lowest points on that line segment. So I need the z-coordinate of this point, and I need the z-coordinate of that point. So as usual, you get the z-coordinate by getting all three coordinates. You get three coordinates from three equations. You get the three equations from saying three things about this point. And the first thing is that it lay in the plane where x was held constant, but now it's also in the line where y is held constant. And finally, it was on the roof, which is the set of points that had equal x and z coordinates. So from these equations, you deduce the coordinates. X is whatever, y is whatever, and then x has to be the same as, z has to be the same as x. So my maximum z coordinate seems to be c, which is a synonym for x. And I guess you guys already know the minimum z coordinate is 0. So it's a lot of verbiage, but it's the same thing over and over again. You are continually looking at a set, maybe holding some of the coordinates fixed, but every time you fix some of those coordinates, you look within the remaining set at the values of the next coordinate. Pick out the points that give you the least and the greatest values of that coordinate. Describe what you know about that point by giving a sufficient number of equations. Solve the equations until you figure out what the magic coordinate is, and then you can write that coordinate into your limit of integration. Having done that, now the actual calculation of the integral is pretty easy. I won't say it's a snap because you got some steps to go through, but we can do this. I mean, here you have a function of z, which you need to anti-differentiate with respect to z, and then plug in these two values of z. So let's do that. I will leave this part unchanged, and I will leave the next part unchanged. But inside, I will say, okay, I can anti-differentiate this with respect to z, because remember, x is constant. Sorry, 4z squared plus x times z, and you plug in your two limits of integration, z equals both 0 and x. And when you're done, what you will have inside the braces will be 4x squared plus x squared minus 0. And that's what you need to integrate with respect to y and then with respect to x. So now I can perform this integral with respect to x very quickly because this is a constant if you're integrating with respect to y. And so the value of the integral will just be that constant times the length of the interval. So I'm going to compute the integral kind of quickly here. It's the value of the constant times the length of the interval, which is found by subtracting the larger y coordinate from minus the smaller y coordinate. And that's what you need to integrate between 0 and 1. And finally, and this is an easy Calc 1 integral, I can pull out the 5 without any trouble. What's left will be x cubed minus x to the 4th integrated with respect to x between x equals 0 and x equals 1. I guess you guys know how to do this. X to the 4th over 4 at 1 and 0 will give you a 1/4. X to the 5th over 5 at 1 and 0 will give you a 1/5. 5 times, this is 1/20th, and 5/20ths is 1/4. So there's my integral. By the way, one thing I didn't do here that I try to encourage you guys to do is to estimate what the value of the integral should be before you start. In my present setting, I would say, oh, I see, I'm integrating a function whose values will take on a range of, well, a possible range of values. I mean, the x-coordinate of any point in this set is always greater than or equal to 0, right? All of these points have an x-coordinate greater than or equal to 0 because they're over here, not there. And likewise, their z-coordinates are all greater than or equal to 0 because everything is above the floor. So if the x and z coordinates are always positive, then the value of the function is always positive. So part of my check would be to say that the integral of that function over that set should be greater than or equal to 0, and it is. In the other direction, well, just how big can this values of this function get? My x-coordinates can get pretty big. In fact, we've already established that they get as high as x equals 1 right here. And the z-coordinate, well, that's asking about the heights of the points, and the highest point is this point right at the kind of at the front of the figure. That's a point whose z-coordinate is actually equal to 1. I guess we figured that out before. This is the point 1, 1, 1. So if the z-coordinates are less than or equal to 1 and the x-coordinates are less than or equal to 1, then the value of the function is always less than or equal to 9. So the value of the integral is at most 9 times the integral of 1. And when you integrate 1 over a set, remember, you're chopping the set into a lot of little pieces, and you multiply the value of this function, which is always 1, times the volume of the little piece. When you add that together, what you will get will be the volume of the whole thing. So this is going to be, at most, the value of my integral should be 9 times the volume of the set S. It's a little tricky to figure out the volume of the set S. I might estimate it by saying, look, you could put the whole thing in a box that goes from 0, 0, 0 to 1, 1, 1. Just stretch out 1 unit in each direction. That would make a big box that would hold the whole thing in it. And it would contain, if it contains my figure S, then the volume of the box is more than the set S. In fact, you can see, you could slice along a vertical diagonal of the box, and my whole figure would fit into just 1/2 of that. So without doing a whole lot of work, I would say that the volume of the set S is at most 1/2. So I was expecting an answer of no more than 4.5. I got an answer which was actually much smaller. Well, at least I'm in the right range. Why is it so much smaller? Part of that comes because I've way overestimated the volume of the set S. It's not too hard to calculate the volume of the set S, and it turns out to be significantly less than 1/2. And the other reason that I've overestimated is because this 9 here is the value of the function right at that single point, but for most of the points, the x and z coordinates are much smaller than 1, so the value of the function is more often a lot less than 1. So yes, I'm in the right range, but more precisely, I feel more comfortable that my answer is correct because I'm at the low end of this range. All right, a good rule of thumb, especially those of you who are in the sciences and engineering, you should always be thinking that the integrals are helping you calculate something useful. You should have, in whatever application, you should have a seat of the pants estimate as to just how big of an answer you're expecting. So always compare your numerical values to some kind of reality check. But there's two things that I want as a takeaway from all these calculations. One is Fubini's original idea to calculate this volume, this integral, by chopping up the set S in a very particular way. Fubini's idea was to chop it up by making slices that were perpendicular to the 3 axes, because then the little pieces into which you've separated the set S have easy to compute volumes. The volume is easy to compute because you just multiply the lengths of those 3 line segments, and every one of those line segments is just how much you have varied one coordinate or another. That's what turns it into a triple integral in the first place. This is your little volume element, is the way people refer to it. And the second big takeaway is, remember how I'm getting these limits of integration. It's a steady process of potentially holding some of the coordinates fixed, looking at all the points in the original figure that have those coordinates at a fixed value, and then scanning for the values of your next coordinate, looking at the points that have the maximum and minimum values of that coordinate, and actually calculating those coordinates by means of writing down the right numbers of equations. Now, if you take those perspectives unchanged, then you can apply this idea of calculating an integral as an iteration of one variable integrals. You can do that in other coordinate systems besides Cartesian coordinates. You asked me about cylindrical coordinates at the beginning, and I can try to get there, but with the 17 minutes left, I don't know if we can make it. I'd like to start instead with an example in polar coordinates, just so you can see a different coordinate system at work. So let me illustrate this by asking, let's try to do a very simple two-dimensional integral, but I'll do it in polar coordinates instead of Cartesian coordinates. So the one I want to do is, let's go back to exactly the floor of the figure that we have been looking at for the last half an hour. That was the region that was bounded by the two curves, which in Cartesian coordinates can be expressed by saying there's the line y equals x, or the line segment that's part of that, and then the parabola y equals x squared. If that's the set S, what would happen if I asked you to compute the area of this set S? That's what you get by integrating the constant function 1 over the set S. Take this set and let's split it into a bunch of little parts in exactly the way that Fubini suggested. And then I will multiply the value of the function, which is always equal to just a 1, times the area of one of these little pieces. Well, you get the area of the little piece by seeing how far you varied in the x direction and how far you varied in the y direction, and you multiply those two things together. You need to sum, or integrate, over a lot of little changes in x, If you add up all the changes in x while you're holding the y coordinate fixed, that will give you the integral over this much of the figure. In other words, it'll be the integral of 1 across just this one row of little squares. And then you further sum over all possible values of y, and you'll add up the other rows. Okay, great. I think when you do this calculation, this is a simple Calc 1 kind of thing. You're taking x going from 0 to 1. So this is the x coordinate goes from 0 to 1, and the y coordinate will go from from x squared to x. When you compute this double integral, it's kind of a no-brainer. It's the kind of thing you computed in a Calc 1 class. I believe you get an answer of 1/6. That's not interesting to me. What is interesting is that we didn't have to do all of the calculations in Cartesian coordinates at all, and we didn't have to split the set up using the coordinate system, Cartesian coordinates, as a guide. You could, for example, have drawn the same picture, but expressed everything in polar coordinates. So for example, this straight line or it's actually just the ray of it, that describes one edge of our figure can be described in polar coordinates as, hey, this is the set of points where the polar coordinate theta has a fixed value of pi over 4. The other curve looks a lot messier to express in polar coordinates, but I can do it. We've talked about how to transform a curve that's given implicitly in Cartesian coordinates to a curve that's given implicitly in polar coordinates. All you got to do is substitute in the formulas that you know that express Cartesian coordinates in terms of polar coordinates. So we have r sine of theta on this side, r cosine of theta on this side, of course has to be squared. So multiply that out and divide both sides by r, and then solve for r. And this would be the formula that expresses the relationship between the r and theta coordinates. So this curve is now actually given explicitly in polar coordinates. For each value of theta, you have a value of r that you can compute. And that's just to describe the curve that's on the edge of my figure. Of course, I want to know about the interior of this picture as well. And I'm going to have to take that set S and split it into a bunch of little pieces and so on. But now that polar coordinates are at foot here, why don't we partition this set by looking not at the sets of points where x and y are held constant, but instead I'll look at the points where r and theta are constant. Here's already one straight line of points where the theta coordinate has been held constant. If I look at holding theta equal to any other constant, I'll get a different ray through the origin. So this is equal to some single value of theta, here's another value of theta, and so on. Then separately from that, I can partition this region by looking at the sets of points where r stays constant. Obviously r is equal to 0 here. I guess you know, since this is the point 1, 1, you can calculate the distance from the origin. This is part of the circle where r is equal to square root of 2. But for any value between 0 and root 2, you can draw the circle of that radius as well, and you get other curves. So r equals r1, r equals r2. And what these curves and rays allow you to do is to separate the original figure into a bunch of little pieces, exactly the kind of thing that we want when we want to start computing an integral. So exactly as before, you can use Fubini's idea to say that this integral can be written as a double integral, where I will let my theta coordinates vary from something to something, and for each theta, I'll let my r coordinates vary from something to something, and I will pick a point inside each one of these little ranges and evaluate this function at that point. Of course, I'll just get a 1. And then, now here's the key part, I need to multiply by the area of this figure. To get the area of such a figure, it's a little tricky to do, but you can get it by approximately, at least if I were to straighten out this edge just a little bit. There's a small variation here between trying to follow the ray that came out from the origin versus trying to follow a line that's parallel to this first line. Obviously, these two lines are not parallel. But making this edge parallel, that changes the area a little bit. Not so much that it's going to affect the integral, though. So when I start talking about how big one of these little portions is, it's okay for me to look not at the area of the part that's getting, the picture that's getting wider. It's okay to just talk about one that stays at a constant width. And then you have something that almost looks like a rectangle. I mean, it's got slightly curved sides, but that turns out not to matter for our purposes. To get the area of such a figure, all you would do is you would multiply the lengths of the two sides, the arc length over here and the straight line length over here. Arc length is off a little bit, but again, it doesn't matter in the limit as the sizes go down to 0. So I would describe the length of this line segment as saying, hey, it's the region where R has varied from R2 to R3 or whatever. So you've got a small change in R, which is a length, and it's the length of this line segment. It's the length of one side of this almost rectangular region. The tricky part is when you go to calculate the length of this other side of the figure, you don't get that by just subtracting off the two values of theta. If you subtract off a certain number of radians minus another number of radians, you haven't got a length. I actually need to know the length of this arc, not the number of degrees or radians involved. And the formula that you may remember from high school geometry is that to get the actual length of the arc, what you do is you measure the amount of angular change, but you have to multiply that by whatever the radius is of the circle that this is part of. And again, there's the front circle and the back circle, and they're slightly different radii, but the difference isn't going to matter when we do our calculations for integrals, because we're going to take limits when these things get tinier. But you do need this factor of R in there. If you multiply a number of radians times R, R carries units of length, and so this will be a length, and that will be a length. The fudge factor of the R is in there to account for the fact that when you move further away from the origin, in other words, you increase the value of R, clearly this little figure is going to have a greater area than the one that's over there, even if they have the exact same length of this line segment repeated here, and they obviously have the same number of radians different between their left edge and their right edge. So the dr is the same in this picture and that one. The d theta is the same, and yet somehow the area has to be bigger. And it turns out that there is this fudge factor of an r that goes in there that exactly accounts for how much the area changes, or exactly accounts for how you compute these little units of area in a figure like this. So we're still using Fubini's idea of splitting up the set S into a bunch of little pieces that are lined up with the coordinate axes, or more precisely, you look at the sets of points where one coordinate or the other is being held constant. And those curves demarcate the boundaries of the little regions that we're going to use. Then we go Fubini, and we just keep multiplying values of the function times the areas of all the little sectors that we've created, and we sum them all up to get the total. So it's just like what we did with Cartesian coordinates, but you do need to understand that there is a fudge factor that comes out to be an r in this case. In other coordinate systems, it's going to be a different fudge factor, and that's what we're going to be talking about next time. But for right now, just run with it. It turns out to be an r. The rest of the calculation involves finding the limits of integration. And that part is addressed in exactly the same way as we did it in Cartesian coordinates. If you want theta on the outside, you need to scan your whole figure looking for the least and the greatest values of the theta coordinate. Your minimal thetas correspond to going clockwise in the figure, and your maximal thetas are found by going counterclockwise. You have a grand tie for all the points with the maximal theta coordinate. They are all the counterclockwise most points, and they all have a theta of pi over 4. Your clockwise most point, the only thing that's left when you go is clockwise all the way to 3 o'clock, is going to be the point that has a theta coordinate of 0. That's the origin, and it has a theta coordinate of 0. Then you fix your theta coordinate, which means now you're restricted to lying on just one ray, a line segment in one ray, and within that set, you indicate the least and the greatest values of the r coordinate. R is minimal when you go as far to the origin as you can, and in this case, we can go all the way to the origin. And the point with the maximum r coordinate is the one that's furthest from the origin. I can see it. I can describe it. I can describe it by saying, well, I've got theta equal to whatever that constant value is, and what makes it be what it is that it's on the outside edge, which means that it has this r coordinate. So two things that I see about it have given me two equations. Take those two equations and solve for the two coordinates. Well, they're already solved. And when you read off the r coordinate, now you have your upper limit of integration. Since I'm out of time, I won't actually compute the integral. We already know what the answer is supposed to be. But what I wanted you to see is how you could get your limits of integration by asking exactly the same questions about the points. Hey, what are your various coordinates? What describes what you are? What equations can I write down that describe you? So this is how we're going to play Fubini's theorem in other coordinate systems. And the two things we'll have to address, we'll do this more next time, are we do have to keep practicing how to get our limits of integration. And we have to figure out why that fudge factor of r is in there, and what are we going to do in the cases of other coordinate systems. All right, I know I ran over, as usual. You guys have any last minute questions that you want to pose to me? Oops. Yeah, Paul, go ahead.
Dr. Russin, can you hear me now? Or
Yeah.
no? Okay, the integration factor of r, are we going to go over that next class for how you got sine over cosine squared? I'm a little confused on that section.
Oh, that sine of theta, well, two things. So let me put the camera back at it if I can. Sorry, I'll just put this thing down. I jury-rigged a document camera for myself, and it doesn't always play well. The reason that this is in here is simply because this is the largest possible value of the r coordinate that I can get anywhere in my set after I've held the theta coordinate constant. And that came from staring at this and saying, oh, yeah, if you want to have your maximal r coordinate go as far from the origin as you can. If you're stuck with a fixed theta coordinate, you can only keep going until you hit the curve. So when you're on the curve, you know that your r coordinate is expressed by this formula. So if you're asking why this expression is here, it's here because it was here. Now, if you're asking why did it show up here, that was the question of how did I convert a curve that was given in Cartesian coordinates into a curve that was given in polar coordinates. So that was a combination of just substituting in those transformations.
Okay.
Yeah?
That makes sense.
Okay. Anybody else? All right, have a look at the first couple of sections of chapter 6 and read through that before we get together next time, because it takes a little while to get used to all that stuff, but you'll see we're going to discuss transformations from multidimensional systems that'll help us describe other coordinate systems. It'll be fun, trust me, it'll be fun. Oh, Yang Zhu.
Sir, I want to ask, where is the integration with changing coordinates system in the book? Like, I cannot find the corresponding chapter, corresponding section.
The stuff in the book that corresponds to this?
Yes.
Oh, that's all of chapter 6. I mean, let's see. Here, it's this change of variable theorem, section 6.2. I know it's fuzzy. I don't know why, but I know this is coming in fuzzy. But this is this calculation that I just did. When we get to this change of variable theorem, I will show you that there is this extra fudge factor in here, which in the case of using polar coordinates this is the thing that's actually going to give us the R. So I'm on page 319 here. That's section 6.2. And it will include polar coordinates that we just worked on. That's the special case of what we're going to be doing. So 6.1 and 6.2, that's the answer to your question.
Thanks.
Anybody else? All righty, guys. Thank you. I'll see you again on Wednesday.